Scientific computing support at the Swiss National Supercomputing Center. So I'm going to talk about the EasyBuild EasyBuild structure that we have implemented over the years at CSCS to maintain the software stack for scientific users. The outline of the talk is as follows. So I will start with the timeline of EasyBuild, of the usage of EasyBuild at CSCS, then an overview over the CSCS HPC systems and how we use EasyBuild on the systems, which means the MeteoSwiss systems mainly, so for the Swiss Meteorological Service, and PITSDYNE, the main production system, and then how CSCS users can use EasyBuild at CSCS. And last but not least, the Jenkins service that we implemented in order to automate the build and installation of the EasyBuild recipes at CSCS, with some final remarks. So the timeline of EasyBuild at CSCS is as follows. It started, well, before 2015 we already had about EasyBuild, but then it took some, let's say, some time in order to have it. And when Guillermo came at CSCS, he started working with Petar and Kenneth in order to provide the tool chain for the Cray system, because since our main production system is a Cray, we had the possibility to, let's say, go at scale with EasyBuild once the Cray toolchains were in place. And the first time was the beginning of 2015. Then there was the installation of a MeteoSwiss systems, a Cray CS Storm, and the software stack of the system was built completely with EasyBuild using the standard tool chains. At the time it was GM Wolf actually, so based on on Mvapich and GNU. And that was the second half of 2015. Then we had an hackathon, the 11th EasyBuild hackathon hosted at CSCS, and finally Kenneth and Petar provided the final stable support within EasyBuild for the Cray tool chains. And over the time then we went over more and more automation using EasyBuild. So we had a major upgrade of the main production system in 2016, at the end of 2016, where all the software stack was built using the EasyBuild recipes with the Jenkins server using GitHub for pull requests. In 2018, thanks to our colleague Theo, we implemented pipelines in our Jenkins service, which enabled to have a smoother interaction with the service and an optimization of the resources. And in 2019, we went through an update of the MeteoSwiss system to Red Hat 7.5, still implementing the recipes with EasyBuild. And at the end of last year, a major operating system update of the Cray system PITSDYNE to the Cray Linux environment 7.0 Apple 1. Finally, in January this year, 2020, we had a new MeteoSwiss system that started pre-production at CSCS. And for this one, we had to implement some kind of manual hierarchical module system because we couldn't unfortunately have L model in place. So now I will go talking about a bit more deeply of the HP systems that we have. So I mentioned PITSDYNE, which is the flagship system at CSCS, and it's used by the user lab. It features most of the nodes, almost 6,000 nodes, I think, that are Cray XC50, so featuring 1 Tesla Pascal per node, 1 GPU per node, and a Cray Haswell processor. And it has some, let's say, 1,000 nodes of multi-core architecture without GPU and 2 Intel Broadwell processors. Then we have the current MeteoSwiss systems in production that are called SCHA and Cache, and our Cray Storm architecture, and recently updated to Red Hat 7.5 with 16 GPUs, still the K80, the Kepler K80 per node. And the new MeteoSwiss system, which is called Arolla and Tsa, these are logical names for the same system, that features 8 Volta GPUs per node with an Intel Skylake processor. Last but not least, we have an OpenStack service, which is a virtual system called Fullen, based on Intel Broadwell and Skylake processors and Red Hat 7.4. So
The MeteoSwiss production system is dedicated production system for the forecasting service. And Esh and Cache, the two systems that I already mentioned, are two identical systems that are used, one for production and one for as a failover with CS Storm nodes. So as you see in the timeline, the software stack is in production with EasyBuild since September 2015. And there were some issues initially, let's say like GCC didn't provide the correct optimizations for the Haswell processor, which had to be fixed. More recently, we have also successfully updated the operating system to Red Hat 7.5 in May last year. Just the summary of the architecture, as I said, probably already, it is based on Intel Haswell processors, so 2 processors per node on a total of 12 nodes, so total of 24 processors on the two systems. We have also FAT nodes, like 256 giga memory per node, and the 8 NVIDIA Tesla GPUs. The new system instead is a single one with 2 logical names, so to ensure more flexibility during the production and failover phases. The compute nodes feature Intel Skylake processor and a Tesla V100 GPU. And as I mentioned in the timeline, the software stack is in production with EasyBuild, in pre-production with EasyBuild since January this year. So I mentioned that we implemented a kind of manual hierarchical way of handling with modules, since unfortunately the machine started without LMOD due to the lack of Cray support to LMOD. So Cray still supports the standard module framework, version 4.0 at the moment on this system. And since it is quite inconvenient to manage multiple modules programming environment at one time, we define some kind of meta modules that are listed here. So programming environments like for GNU and PGI mainly, that opens up, like loading the module path, another set of modules at a lower level, let's say. So what you would say, loading the program PGI will be the following with HDF5, NetCDF. So the dependencies that are usually needed to build the Cosmo climate software. We mainly rely on PGI now because they use Open ACC in the code, and Cray has also dropped support for that. So in the past we used the Cray compiler, and we had also a programming environment Cray that was more or less imitating the one that we have on the flagship system. Now we drop that on the MeteoSwiss system. So technically we could drop completely the Cray software stack here, although it's still present on the system because in production it's no more used. And at this point I was thinking we could probably go also with LMOD if our system administrators will support it, because there is no reason anymore since we are not blocked by Cray, but that's to be seen. So Pitstein, the production system, is a hybrid system. So most of the nodes are hybrid, Cray XC50, and some 1,000 nodes are Cray XC40. So I already mentioned, so the multi-core architecture is featuring two Broadwell processors, and the hybrid architecture is featuring a Haswell processor with a Tesla GPU, a Pascal GPU, Tesla P100. Login nodes are fat for compilation and building. Most of our building takes place, in fact, on the login nodes for EasyBuild recipes in production with Jenkins. The interconnect is based on a Dragonfly network topology with areas routing. The sketch file system is 8.8 petabytes and is a Sonexion 3000. So the user lab uses this system as it is configured now since 2016, successfully with EasyBuild recipes that we also provide to users in order for them to automate their installations of software that we don't provide already on the system. And recently, our colleague Irini implemented a set of scripts in order to automate immediately the EasyConfig files in upgrades, which helped a lot in the latest operating system update to Cray Linux Environment 7. Currently, work in progress. Guillermo submitted, I think, a pull request, but we're still testing it. Create a toolchain called Cray Intel MKL in order to use the MKL directly, because the Cray system features scientific libraries in a module called Cray libsci that sometimes is not as fast as Cray MKL. and people using the Intel compiler wants to use directly MKL. Sometimes it just requires a module unload, but could be easy to use a dedicated toolchain. Just to give you a feeling of what we have on this system, so we provide a lot of scientific software built with EasyBuild automatically. Most of the software that I put here is installed with GPU support. So you see in the name of the module file provided by EasyBuild the CUDA version suffix. At the moment we have on the system CUDA Toolkit 10.1. And most of the software is built with the GNU or the Intel compiler in the toolchain called Cray GNU or Cray Intel. Both these toolchains use scientific libraries, the Cray libsci. Some of the Intel recipes here, like Quantum Espresso, switches to Cray MKL just manually in the easyconfig file. So once we will have the Cray Intel MKL ready, we might use that instead. So what do users do then with our EasyBuild installation? In general, when users ask for software that is not already provided on the system, we try to give them an EasyBuild recipe in order to, let's say, reduce error-prone manual steps and also to improve our, let's say, the management of the support to the users, instead of giving just manual recipes that are difficult to track also for individual requests. Then the users can manage their installations with some documentation that we provided on the CSCS user portal in order to compile their code. So they load a custom module file for EasyBuild that we call EasyBuild Custom CSCS that loads in turn the EasyBuild module file and just sets all the paths and the variables that are needed to build on their home, the software that they require. And in general, this framework is working, let's say, pretty efficiently for individual requests. Of course, if we have requests from groups, in general, we support directly the software installation. And that's done through Jenkins, so the Jenkins service that is in place already for a while, since 2016, and then implemented with pipelines in the past 2 years. So we use it for continuous integration of our software recipes with the production system. So we test the pull requests submitted either by CSCS staff or by users that could submit to our GitHub production project. And then once the requests are merged, then they are deployed, so installed directly on the systems in production. We have also in place a weekly regression test in order to check for reproducibility. So the names of the Jenkins projects are available on our internal Jenkins servers, and we call it EB testing, production, and regression. And as I mentioned already, the testing is triggered every time you submit a pull request to our repository. So matching for system names and EasyBuild recipes. And then after successful merge, the EB production project takes over and it builds the merged recipe in production, on the production system. And the weekly EB regression then tests completely from scratch all the recipes that we have in order to check the download, if the download still works, if the installation is still successful. And finally, the pipelines defined in the Jenkins service enhanced a lot of flexibility of the actions in the sense that they could, first of all, we have some scripts that are version controlled. We can check all the modifications, and then the CI can also run in parallel, so we can optimize the workers that we have on the different machines. On the production repository, on the GitHub production repository of CSCS, you will find the rules to submit a pull request that basically just give you some hints on how to start a template for your pull request, like the subject needs to fit, that it needs to show the name of the system that you are applying your recipe to. So the users in general are targeting the production system PITS-DAINT. Then you need to, of course, assign a reviewer and the usual stuff for pull requests. On top of that, we have sometimes, in case of the flagship system, different architectures. So for PITS-DAINT, we have the GPU nodes, the multi-core nodes, so you have also to tackle these two architectures in the pull request. Once the request is approved and merged, your software will be built in production if it's put in the production list. Now, the process goes as shown here. So you submit a pull request on the GitHub interface of our production project. Then you see on the right side the Blue Ocean interface of Jenkins that shows you the starting, that is the pipeline triggering the run in order to test your new EasyBuild recipe on our architecture. In this case, it's the GPU architecture of PITS9, the GPU node. So as you see, in the case of recipes that should run on multiple architectures, like you want to have your software on both the multi-core and the GPU, then you can just submit a pull request that triggers both tests, and you see that in the Blue Ocean interface of Jenkins, in parallel, it tests the build of the EasyBuild recipes on both nodes. And finally, the regression pipeline, so the weekly regression, so everything. We have now almost 4,000 custom recipes in the CSCS production repository on GitHub that we test weekly. Well, not all of the 4,000, because we have a restricted list for the real production stuff. So most of the individual user recipes are not really tested because they are maintained by single users. So it's up to them to test them. But we test the main production software stack. And we test in parallel that on all the systems. So this is an old screenshot when we had some more systems that are no more with us. And it's beautiful to see all the green thing. It's very rare to see that recently, but anyway, with many upgrades, sometimes it's difficult to keep track of all the things. And then final remarks. So these are general remarks. Moving to, let's say, to EasyBuild is it's not immediate. It takes some time, of course. There's a learning curve for the staff and then for the users as well, and some resistance to change, as usually it happens when you have something that you have traditionally been doing and then you need to change. But it's, of course, the advantage of the automation is for sure the most important thing, and the community behind that. So in our personal experience of EasyConfigs versus EasyBlocks, so EasyBlocks are usable, they are great, well packaged, but they carry sometimes some overhead if you want to modify that for bleeding edge software or for new software. And also for reproducibility, sometimes we find it easier to deal with EasyConfigs. So that's why we tend to use mainly EasyConfigs, and we have not so many custom EasyBlocks in our production repository. Just because the EasyConfig gives you also the possibility to pass that to the user a completely self-contained recipe, and the user can easily see in the EasyConfig all the steps, while the EasyBlock sometimes hides important steps in the installation. Talking about developments that were, let's say, improvements in our management of the software stack. As I mentioned, in the new MeteoSwiss system, we have now fully automated the deployment with this manual hierarchical module environment until we will have a Helm mode, hopefully. We used mainly FOSS and FOSS CUDA 2019B. So we have their post-processing nodes and GPU nodes as well. So we use the two toolchains with the two software for the two different nodes. Just the custom thing, we usually use the stock EasyBuild recipes for these two toolchains. We only have the custom module naming scheme, which is lowercase, due to the preference of MeteoSwiss developers. Another important thing is the automated recipe conversion for OS updates that I mentioned before, that was tested during the recent update in November of PITS9 to the recent operating system. And work in progress, extend our Jenkins pipelines with EasyBuild and adding a reframe step in order to immediately check the regression test, not only the build and the sanity, but also the performance of the newly installed software. We need then to take care about the naming scheme because they have to match. And some useful links of the documentation on the CSCS user portal and the production repository on GitHub that we also mirror on the main EasyBuilders GitHub repository. So you can find our custom recipes that are useful for Cray systems there. So thank you.
Any questions?
For the software you install for MeteoSwiss, I don't think you mentioned what type of software. Well, meteorological stuff, but is it Cosmos?
Yeah, it's mainly for Cosmos. So as I mentioned in the PG, so they mainly use PGI, and you see mainly the dependencies are NetCDF, HDF5, well, OpenMPI now, because we had some issues with MVAPIC that was traditionally used by them, but now with this recent version.
But you prefer using the ones that are installed with EasyBuild over the ones provided by Cray. Did I get that right?
That's true.
For HDF5
Actually, yes. The reason is that now Cray stopped supporting OpenACC, at least in the new programming environment. So we need to use PGI because OpenACC is used by the Cosmos software, and this was the main reason for switching to PGI. The switch from MVAPIC to OpenMPI was due to some bugs exposed of the code with the recent version of MVAPIC.
Yeah. So you have requirements that Cray doesn't support.
Yeah.
Yeah. And for the software that's unnamed, so they had a long list of modules there.
Yeah, this is just a selection, let's say.
Yeah. How extensive? So the installation is done by EasyBuild, and EasyBuild does some very simple checking, sanity checks, and maybe running a -- help or a very small test case. How extensive is CSCS support testing those installations before considering them production ready?
Well, we have a reframe in place that tests also the performance. At the moment, it's not automated in the sense once we build it, it's not immediately running afterwards, but it's running daily on a different schedule. So what we were thinking is about actually adding this step once we install also, before, let's say, installing the software with EasyBuild in our Jenkins pipeline in order to fully check, let's say.
Basically including reframe as a step in the Jenkins.
Yeah.
We first deploy in the TDS system. So there, it's easier to have reframe just running and updating just the standard stored prefix from there, and then reframe just taking every time the latest there.
Yeah, the only restriction is the fact that we only have a few nodes on the TDS, but that's fine because it gives you already a hint of what will happen in production.
And that's also, I mean, big relevant test cases, not just small Mickey Mouse things.
Well, the daily test case could not be too long because it should take more or less 10 minutes, I think. The whole regression daily, the reframe daily.
You mean the maintenance
No,
tests?
yeah, okay, the maintenance tests are the longer one. The daily one should be fast, so these are small benchmarks. We have also in place now in reframe much longer checks for several applications, scientific applications that you can run in, well, I think that in the maintenance we still run the fast check anyway.
Yeah, usually for the applications, we had, depending on the, in the TDS we're using 6 nodes, and then we're using 16 nodes, and we have an implicit time limit on how large it's going to be the run of 2 minutes. So 16 nodes, 2 minutes. The test case should not exceed that, just even for the daily runs. Yes.
Not really self, but by our system administrators that don't want that to take too long. But anyway, it makes sense for the daily check. In case we have troubles, we can also have longer checks that are already implemented in reframe for specific selected applications. Yeah, so with large scale and much, let's say, deeper. Also, users can contribute their tests for selected applications in reframe, so that's also important.
Any other questions for Luca?
So thank you for the presentation. I find the Jenkins integration interesting. So what kind of, or how do you basically define build state? Because I guess you run EasyBuild, right? And then you have exit code 0 or 1, or how do you know that the build was good or bad? And also, do you collect some kind of test results in the sense of like it would otherwise be JUnit test results?
So the exit status is collected during the, we run just scripts inside the Jenkins pipeline that collect the number of failures and then report that. So you have a certain list of recipes that are tested inside a certain Jenkins project, and then for each of them you accumulate just the number of the exit status in order to get a final number of failures. So for the log, as you were asking, if we are collecting that, we have the log saved on the Jenkins server and on the system, so both of them, in order to retrieve the actual steps of the installation for each of the software list, for each item of the software list.
Okay, and for the reframe, because I'm not familiar with reframe, unfortunately, but do you get some form of like unit test results for each test case that you can read this again in a structured way?
Yeah. Yeah, okay. I didn't mention reframe here because it was...
Yeah, you said it's in development.
Yeah, we plan to add this step, yes. Yeah.
Okay, cool. Thank you.
The idea of this step is just another... The idea of this is that we just add another... Can you go to the previous slide?
Which one?
Yes, this one, yeah. So another step, pipeline stage of Jenkins there.
Yeah, after build
will
stage.
Essentially run a reframe on the freshly build recipe. So using there is an option in reframe that you can replace the module and just run the actual test. And then everything is logged also there, but also reframe produces a log, which we store it through Jenkins.
Okay, let's wrap up here.